I'm going to be talking about Scalable Public Protection and Disaster Relief Service that we deployed on the Arcadia framework. So just as an introduction, what is public protection and disaster relief? The first thought that we get when we talk about that is, of course, that this is about saving lives. So this is really emergency services, and this is the highest that the stakes can get. And such services are typically provided by emergency response organizations or EROs. We also call them first responders. And typically there are multiple such organizations operating in parallel. So anytime you think about police, fire brigade, ambulance service, civil defense, you're actually talking about public protection and disaster relief. Now, such agencies, such organizations operate on three levels typically. The first one is for everyday stuff that happens all the time. This is kind of the low stakes. Second level is for large events, and the third level is for disasters. So if we put this in perspective with a picture, basically we see that extreme situations, this is the highest that the stakes can get. And this is, of course, it's easy to design a system that operates in everyday situations because there's nothing wrong with connectivity, there's nothing wrong with the backend, with the services. But in extreme situations, such as like an earthquake or extreme flooding or any kind of mass event, you can have problems even there. So you can have communications disrupted or even the data center, the backend. So we wanted to actually use our use case to demonstrate how Arcadia can solve this. Now, of course, when we talk about such services, there's different levels of requirements also from the point of view who's using them. We have strategic level, we have tactical level, and we have the user level. So this boils down to a lot of requirements. I'm not going to go through them in great detail, but we do need high performance, extensibility, we need high availability, especially if a disaster occurs, which would of course mean that we need some kind of distributed system, distributed logic. We want to provide mobility of units, so we want to have people to have connectivity even when they move around. We want to be able in some cases to collect data from them, like monitor them, their life functions, locations, and so on. We want to be, in some cases, to use special equipment such as drones. And last but not least, we want to ensure that there's some interoperability, both in the local. We saw that we have many agencies in the local domain and internationally. And all these requirements basically can be grouped into two categories. We have network requirements, which of course mean we want resilience, low latency, and high bandwidth. And we want some backend requirements, which of course means we need some geo-redundancy, we need some scalability. So if a server is overloaded, we want to have another one established, instantiated immediately. And of course, we want also monitoring. Now, the network part is pretty well addressed using existing and future coming standards such as LTE, 5G, and even satellite connectivity. So in worst case, we can always set up a satellite link and have connectivity even in areas where it's severely disrupted. Here I have a slide showing what 5G is promising to deliver in this area, in the area of network connectivity. So there's a bunch of stuff in terms of, for example, direct mode communications, which means device-to-device communication, vehicle-to-vehicle communication, using different parts of the spectrum, and so on. But there's nothing here about the backend and about the actual service that we want to provide. So this is why we used Arcadia for this part. And I'm just going to go briefly over some of the main points. We've heard a lot about Arcadia today already. What I want to reiterate is that it's meant for deploying highly distributed applications. And this is exactly what we're going to be using it for, to make something highly distributed, to bring it beyond a single data center. Now, there's two kinds of building blocks, two kinds of bricks in Arcadia. We call them native components and wrapped components. Native component is something that is developed from scratch with the Arcadia mentality in mind. And unfortunately, what we have is a lot of existing building blocks in our use case, which means stuff like open source databases, MySQL, and similar components. They can't be developed from scratch. They can only be reused. And this is why we opted for the second approach, which is wrapping them. And we basically provided a small thin layer that communicates between the component and the Arcadia controller. Now, I'm mentioning Arcadia controller. That's the brains of the system. This is the part that actually does all the hard work of monitoring stuff and responding to what's going on. So basically, we're going to be using that to define some policies, some rules that allow us to go beyond, like if something happens, to make new instances, to go to a different data center, and so on. So here's, for example, a screen of how for example, rules can be defined, how these policies can be defined. So it's basically if then, if this happens, then do this. And this is basically how the controller works. Now let's talk about how we deployed, how we moved our application to the Arcadia framework. Now this is how our application looked before. This is a 6-in-action monitoring, 6-in-action application for intervention monitoring. And before it was basically developed as a monolithic web app, which means you see down there, there's a database, there's a web server, and there's some file storage for storing uploaded materials. And of course, it provides two different interfaces to the outside world. The first one is a web GUI, and the second one is REST APIs for mobile apps. So this basically connects first responders with personnel back at the emergency response organization. Now this is how it looked before, and we needed to do some work, of course, to port this to Arcadia. Now, this monolithic architecture had some drawbacks. First, it was a single point of failure. It was living in one data center. It was deployed on 2 VMs that were not elastic in any way. They had limited scalability. Basically, the scalability consisted of shutting down a virtual machine and adding more resources and powering it back on. So this was in terms of vertical scalability. In terms of horizontal scalability, of course, it was not possible because the components were tightly coupled. And first, we of course needed to decouple them. Now we also had limited monitoring, which means mostly manual inspection of stuff like Munin metrics or getting some Nagios alerts, but it had to be done manually. So we wanted to optimize all three parts using the Arcadia. And of course, this is what we achieved by porting it to Arcadia framework. We ensured high availability, we automated the scalability part, and brought some dynamic adaptation into the picture. So there's just some briefly how deployment like this works. So basically, there's the part behind the scenes. Of course, we needed to split the components into independent blocks and remove the state. And this, of course, allowed us to make one part horizontally scalable, because it was just a dumb worker from the new point of view. And how we deployed that, of course, we selected the necessary components, specified for each one of them how much resources they need, specified the parameters they needed, such as passwords and usernames, network parameters, the IP addresses. Then we placed all of the components in a service graph and assign dependencies, specify the level of distribution, set the policies, and press the deploy. So this is how it's supposed to be at the end. Now let's take a look at our service graph. It's kind of complicated here, but you see that it's in two different data centers. The red blocks are data centers. So what we wanted to do was to make replication work across data centers. So basically the same setup is deployed in two data centers, and the data is moved across using, in one case, MySQL replication, and in the other case, we're doing a file sync using a sync thing. And this is the final picture of how this works. So you can see here, the yellow building blocks now are the stateless web servers. So this is the stuff that we can horizontally scale. We can just add more. And once they wake up, they have no state on them. So basically all the state they use, they can get it from the database and from the file storage or the blob storage, which means, of course, this is not a bottleneck anymore. Now, MySQL, of course, is just one per data center, and we scale it vertically, basically by shutting it down and adding more resources and restarting it. But we do have a hot spare, so to speak, in another data center. And now the Arcadia controller is monitoring both of these, adding resources as per our policies, and also both of the apps, the web app and the mobile apps, are now connecting to either one of these, which they do using DNS round robin. So this is now our service graph. This is just example for one data center. So it's a service graph with dependencies. And now let me briefly show you how our scenarios work using the rules we defined. So the first scenario is horizontal and vertical scaling based on the server load. So this is now our client here. As you see, our client is querying the DNS, and based on the response it gets from DNS, it connects to either one of those workers, and those workers, of course, are backed by shared state. So they can see the same things. They can see the same database and the same files. Everything is synced across two data centers. Now, what happens if we get high CPU load here? Or if you get low disk space warning on the blob storage? Now, the controller is going to see that, and of course, it's going to add more resources. And it's going to add more resources like this. So basically what it does, I put the building block down here. It instantiates a new web server. It's a stateless one, so it's just backed by the same data, and it can just start serving requests. And now the web server that just woke up, of course, is not yet in the DNS. So it's going to ping the DNS, so to speak. It's going to call an API of the DNS to add itself to the record list, and now client can make round robin between all three. And pretty much the same mechanism is reused in the case of a data center outage. So in the case of a data center outage, what happens is we lose the whole data center, and this is something that might happen during an extreme event, during a disaster. So what you want is geo-redundancy and the second data center somewhere far, far away. And what happens now is, of course, also the sync is gone, but the last state, of course, is in the second data center as well. And now this data center can't handle the load, which of course means that now the controller is going to also add resources here. And now the resources are going to register themselves, and we can again do the round robin. So this is how we handle both of the cases. Now there's many metrics that we use when deciding what to do. And those can be either the virtual node metrics, such as CPU load and stuff like that, or they can be application metrics. such as how many queries per second is the database making, what's the slow query response, and so on. So this is going to be a really flexible way of deciding when to increase resources and why, and how to do it. So this is all from my side. Thank you for your attention.